Yes, so in the last class we have derived terminal velocity. So 2 capital R square G rho minus sigma by 9 eta. So eta was the coefficient of viscosity. Now, depending upon the density of the body and the liquid, we have to determine whether the body will sink or will it float. So see, when rho minus sigma is positive, this means terminal velocity will be positive, right? This is green. Terminal velocity will be positive. Look, rho minus sigma. Rho minus sigma, if this term is positive, this will be positive. If this term is negative, this will be negative. So rho minus sigma is positive here. So terminal velocity will be positive. In this case, body will move downwards. Then you have, if sigma is greater than rho, so rho minus sigma, if this term is greater, it's like 1 minus 2. It will always be minus 1. 1 minus 3, it will always be minus 2 because this term is greater. So when density of liquid is greater, this will be negative. So your terminal velocity will be negative. So body will move upwards with the negative terminal velocity. For example, air bubble in water. Air bubble always moves upwards. Why? Because water's density is greater than air's. But when we're talking about water drops in air, if the opposite we take, water drops always fall down. Raindrops, you can take the example of raindrops. Because density of the body is greater than the fluid. For us, fluid now is air. Let's see a question also. First, write this down quickly. Yes, so this question says a water drop in air has terminal velocity of 100 meter per second. 8 such drops combine to form a bigger drop. You have to find out the terminal velocity of bigger drops. So terminal velocity of smaller drops are given. Terminal velocity of bigger drops is calculated. It's like these 8 drops, they are combining and forming one bigger drop. So this radius must be smaller and this radius must be capital R. So one thing that will remain constant is the volume. Volume will not be changing. Okay. Volume will be remaining constant. So volume of 8 small drops is equal to volume of one big drop. All right. So 4 by 3 pi small r cube, 8. 8 into 4 by 3 pi small r cube is equal to 4 by 3 pi capital R cube. 4 by 3, 4 by 3 cancel. So 2 small r is equal to capital R. One thing class, terminal velocity, this is directly proportional to R square and we just need relationship between the radius and terminal velocity. So terminal velocity of small radius is equal to small r square by terminal velocity of bigger is equal to bigger's radius square. So we have this relation. Let us substitute this here. So V small r by V capital R, this is R square. This becomes 4R square, R square, R square cancelled. So the bigger terminal velocity is 4 times the smaller one. That is 4 times 100. So this is 400 meter per second. Clear? Are the steps clear? Yes? No? Do you want me to repeat? Mariam? Nuha? Am I audible or not? Yes, Mariam and Nuha? Is this not audible?
Yes, ma'am. I can.
So why were you not responding? And what about Nuha? Nuha has still not responded. Are you not there in the class, Nuha? Write it down.
Ma'am, I changed my device, so I wasn't
Okay, okay,
able
okay.
to.
Okay, okay. Yes, now coming to fluid flow. So this is a very small topic, but important one. When there are certain assumptions while we are considering the fluid flow. So these assumptions we'll study better uh, in kinetic theory. All right, so that is also left kinetic theory. So that time we'll study. So the fluid is non-viscous. There is no internal friction between the adjacent layers of the fluid. The fluid is incompressible. This means that density of the fluid is constant and the fluid motion is steady. So these are the assumptions we assume when the fluid is flowing, non-viscous and all. So, but we'll see all the postulates in kinetic theory. So let's leave this first. Types of fluid flow, let's study. Streamline or steady flow. The flow of a liquid is said to be streamline flow or steady flow if all the liquid particles that pass any given point follow the same path at the speed. See, streamline flow means this type of flow. Now see, if I say at this point, any particle will come, let's say this is A point, this has to have a velocity of 30 meter per second. Now, whichever particle will be coming, at this point, it will be having 30 meter per second. Let's say at this point, this is B point. So VB, let's say this is 40 meter per second. So at any point, this will be coming. Any particle will be coming. This will be experiencing 40 meter per second. So same path, if this is turning, if this is, there is a curve, this is turning. So like this, VA, VB, and VC. So this is known as streamline. When all the particles follow the same speed, see, at this point, if it has to be 40 meter per second, so any particle is coming, this will be having 40 meter per second, and this will be taking a curved path. This is what is meant by streamline or steady flow. But when we're talking about the laminar flow is a special kind of streamline flow, you can steady flow. All the liquid layers are parallelly arranged like this, laminar flow. Okay. Then turbulent flow. Flow of a liquid is said to be turbulent when there is a disorganization, disorderly flow like this. This is one flow of the particle. This is another flow like this. This is known as turbulent flow. Okay. And what is meant by rate of volume of liquid? Okay, all this I'll tell you later. First, write down these fluid flow. Then we'll discuss the rest of it. Quickly write it down. Okay. Now, rate of flow. This is the volume of liquid that passes the cross section of a vessel in 1 second. This is known as rate of flow. We represent it by Q. So basically, volume of liquid that is flowing the cross sectional area in 1 second. Or directly, you can write it as A by T. Area is better to write. This we'll see later also. Now coming to Reynolds number. Reynolds number is basically, see, three things we have studied: laminar flow, turbulent flow, and streamlined flow, right? So there's a formula. How do we predict whether it's streamlined flow, turbulent flow, or a laminar flow? So see, you have a concept known as Reynolds number. Density of the liquid, this is the density of the liquid. This is the velocity of the fluid flow. This is the diameter of the pipe divided by coefficient of viscosity. This eta is the coefficient of, this is the coefficient of viscosity. So if this Reynolds number will come less than 1000, then this will be streamlined or laminar. If it is more than 2000, then it would be turbulent. But if the number is between 1000 and 2000, that is less than 2000 or more than 1000, that is between 1000 and 2000, like 1500, like this. So it means it is shifting between streamline and turbulent in between these. So you'll be having the questions, you'll have to identify which type of flow is this. So using Reynolds number, you can easily calculate. One more parameter you have for the calculation, which is the critical velocity. So what is critical velocity? Critical velocity also is a formula. There will be a constant given to you. This is just a constant. It will be given to you in the question. Coefficient of viscosity. This is coefficient of viscosity by rho d. Rho is the density of liquid. D is the diameter of pipe. This is the diameter of pipe. All right. Now see in this, if the velocity of the fluid, this will be less than the critical velocity, it means this is streamline. Velocity of fluid, if it is greater than critical velocity, this is turbulent. Okay. We will see questions, but first you write down this from here. Okay, this says that the flow rate of water from a tap of diameter 1.25 centimeters is 0.48 liters per minute. Coefficient of viscosity, this is how much? This is given 1000. 10 to the power minus 3. After some time, the flow rate increases to 3 liter per minute. So initially it's 0.4, now it's 3 liter per minute. You have to characterize the flow for both the flow rates. So Q initial, this is 0.48 liters per 1 minute. Volume of flow, rate of flow, so 0.48 into 10 to the power minus 3 meter cube. This is how we convert 1 liter into 1 meter cube. 1 minute into seconds is 60 seconds. So this will be around 0.08 into 10 to the power minus 4 meter cube. Q final will be 3 liters by 1 minute. So 3 into 10 to the power minus 3 by 60 seconds. So this is 0.5 into 10 to the power minus 4 meter cube. All right, this is the rate of flow of fluid. This Q is the rate of flow of fluid. So volume per time. But we have to write it in SI units. So this will be meter cube per seconds. Meter cube per seconds. Meter cube per seconds. Now see, rate of flow is volume by time. So volume we can write it as area into length by time. And see, area, this length into time can be written as velocity. So Q is equal to A into V. So what is the volume? Pi r square V. Area is pi r square. Volume is V. So we write it, velocity is V. So we write it as pi d square by 4. Understood? How have we written this? This is the area. This is the velocity. This is the area. This is the velocity. Why area? Area in terms of the radius. So here Reynolds number in this question will be 4 into 1000 into Q we have calculated 0.08 into 10 to the power minus 4 divided by 10 to the power minus 3 into 3.14, and what else is left? 1.25. Yes, 1.25 into 10 to the power minus. So when you will solve it, this will be 815. Now see, when Reynolds number is 815, that is less than 1000. This is a streamline flow. And if the Reynolds number, same thing you will calculate for the second one, that will come out to be 5096, which is a turbulent flow. This is how you calculate. One thing, the last thing, last topic from this section is equation of continuity. If you have velocity and area, because this is a continuation of this only, that's why I'm not stopping right now. Velocity is V1, area is A1. Velocity is V2, area is A2. So what have we studied? That area into velocity is constant. This is what we have seen. Area into velocity is constant. So A1 V1 is equal to A2 V2. This will always remain constant. That's it. Write it down, write down the solution. See, when we are talking about Bernoulli's theorem, so last topic, Bernoulli's theorem, and one very small topic, Torseli's theorem. So these two topics are only left. So in the next class, we'll be able to complete this lesson. And then straight away, we'll start with waves and oscillation. Now you'll be having the classes of kinetic theory separately. Okay, so according to your convenience only, I'll arrange the classes of kinetic theory. Then we'll straight away start with waves. Waves is not a very lengthy lesson. SHM is also not a very lengthy lesson. We'll straight away start with that. See, what is potential energy? mgh. So we'll be writing potential energy per unit mass. That is, this is mgh. So per unit mass means divided by mass. Cancelled, this is gh. And if we write per unit volume, if we write potential energy per unit volume, so it will be U by V, that is mgh by V. See, mass by volume, this is density. So we write this as rho g h. This is about the potential energy. If we are talking about the kinetic energy, so kinetic energy is half mv square. So when we write kinetic energy per unit mass, that is half mv square per unit mass. It's only v square by 2. When we are writing kinetic energy per unit volume, that is half mv square by volume. Again, mass by volume will be density, so it will be rho v square by 2. We'll be using these energies per unit mass, per unit volume in Bernoulli's theorem. That's why I'm writing this separately. Lastly, you have pressure energy. Pressure energy means the work done by the pressure. That is the pressure energy. So basically, we write the pressure energy. We write the pressure energy as P delta V. This is the change in work done. This is the change in work done that we'll be calculating. So Bernoulli's theorem basically says that total energy will remain constant. Total energy means all these three energies. When I say total energy of a system, total energy means the pressure energy, the kinetic energy, and the potential energy per unit volume. All these will be constant. That is pressure energy, potential energy per unit volume was rho gh, and kinetic energy per unit volume was half rho v square. This will always remain constant. This is your Bernoulli's theorem. You have a proper proof for that. You have a derivation for Bernoulli's theorem, but this is all about Bernoulli's theorem. First, write it down. Yes, class, you can leave. Now we'll continue this in the next class. Okay, the derivation is left and Torricelli's theorem. Okay, thank you so much.